Hello there, and welcome back. This is Fall Asleep to Science. Tonight we turn toward a world we think we know, yet half of it has always been invisible. You've seen the moon 1,000 times. Its familiar face rises above the horizon, glows through thin clouds, hangs quiet above the sea. The same seas, the same craters, always staring back. But what about the other half, the far side, the part that never looks our way? As you rest, imagine the moon as a slow companion orbiting the Earth, bound by an ancient rhythm. One side forever turned toward us, one side forever hidden. This is the far side, not dark but unseen, bathed in sunlight half the time, just like the near side, yet unseen by human eyes for all of recorded history. It turned silently for billions of years, its craters untouched by any glance from Earth. Before spacecraft, it was a place of speculation and imagination. Poets thought it a mirror of paradise or a realm of mystery. Astronomers wondered if volcanoes still burned there, or if perhaps the moon hid secret planes unseen from our telescopes. For millennia, no one knew. Then, with the age of rocketry, that veil began to lift. NASA, and before them, the early Soviet missions sent metal eyes into orbit. The first photographs of the hidden hemisphere returned grainy but profound. They revealed a world scarred and ancient, a land of deep craters, fractured ridges, and almost no Maria, the dark lava plains that make the near side so recognizable. Beneath that rugged face, instruments would later find strange signatures, dense concentrations of metal, strong magnetic traces, and hints of frozen water locked in the moon's coldest shadows. The far side was not just unseen. It was different, older, thicker, more silent. A geological counterpoint to the face we know. So tonight, as you breathe softly, imagine drifting in slow lunar orbit. Below you, the gray surface slides past. Half of it is home, the side that always faces us. The other half, the far side, waits in its ancient solitude. Let your mind turn with the moon itself, steadily, quietly toward that hidden hemisphere. Before we begin, I'd love to know where you're listening from tonight. Are you somewhere under city lights, where the moon hides behind tall buildings? Or somewhere rural, and still, where its glow paints the grass in silver? Wherever you are, we're under the same sky. And if these calm explorations help you slow your thoughts and drift a little easier, a gentle like or a soft tap on subscribe helps this small corner of the cosmos reach other sleepy minds, one quiet soul at a time. We'll begin with the reason it remains unseen at all, a celestial balance older than human memory. The moon turns, yet it does not turn away. From the surface of Earth, its face appears still unchanging, eternal. Craters like eyes, Maria like shadows, frozen in their familiar arrangement. But in truth, the moon rotates once every orbit. It spins slowly and precisely, in perfect synchrony with its path around the Earth. One rotation for one revolution, one gentle spin for one circuit through the night sky. This condition is called tidal locking, a cosmic stillness born of motion. Long ago, the moon was different. It spun faster, turning freely through the early solar light. Its molten crust cooled under a heavy bombardment of asteroids, and its surface began to harden. But the Earth's gravity, massive, insistent, tugged unevenly on the moon's near side, the side facing us. That pull stretched it slightly, raising invisible tides in its crust and mantle. The friction of those tides drained the moon's energy of rotation. Little by little, over eons of silent time, the spin slowed until it matched its orbit. The moon became locked in step, a dancer turning with its partner so perfectly that the same face is always seen. Now that balance is complete. The moon rotates once every 27.3 days, the same period it takes to orbit Earth. As it circles us, it keeps one hemisphere forever directed toward our sky. This is why the familiar features, the Sea of Tranquility, the Ocean of Storms, the bright highlands of Tycho, always remain in view. It's a delicate equilibrium held by gravity's persistent rhythm. Every moon of every major planet, given enough time, tends toward this state. Tidal locking is the universe's quiet way of saying, slow down, stay close, turn together. And yet the far side is not truly unseen in every sense. The moon wobbles slightly as it moves what astronomers call libration. Because of these gentle oscillations in angle, we on Earth glimpse a little beyond the exact half that should be visible. The moon nods, tilts, and sways by a few degrees, revealing slender slivers of territory near its limb. Through these librations, we can observe about 59% of the lunar surface in total. That leaves 41% permanently hidden, never visible from Earth, no matter how the moon rocks. A hemisphere of history unseen by all humanity until the mid-20th century. For millennia, the far side existed only in imagination. Through telescopes, we saw bright peaks along the moon's edge, mountains catching sunlight as the Terminator line shifted. But the hidden half remained beyond reach. Its geography could not be mapped. Even the best telescopic instruments could do nothing to pierce the geometry of tidal locking. Ancient astronomers wondered if the unseen face might be smoother, or perhaps covered in oceans. Some imagined it as darker a twin world where shadow reigned. Others believed it to be a mirror reflecting cosmic light unseen from Earth. These ideas filled centuries of speculation, a symbol of what lies just beyond our knowing. When spaceflight finally arrived, that mystery began to dissolve into reality. But the quiet balance of tidal locking still holds. Even now, even after spacecraft have photographed and orbited it, the moon keeps turning with that steady rhythm. A rotation that's invisible from Earth but perfectly measured by the dance of gravity and time. If you were standing on the near side, the side facing Earth, you would see our planet motionless in the lunar sky, always there. Sometimes full, sometimes new, but always hovering in the same spot above the horizon. Its blue glow washing the gray dust in soft reflected light. Stars moving slowly across the heavens, but Earth remaining fixed, eternal. On the far side, it's the opposite. The sky never holds our planet at all. There is no Earth rise, no blue glow, no familiar world above the horizon. The stars drift freely unanchored. The sun rises and sets as it always does, but the Earth is gone permanently hidden behind the moon's own body. That is what tidal locking means in lived experience. One side eternal daybreak and shadow Earth overhead like a lantern. The other endless night unmarred by our reflection. Two worlds in one body, one facing outward, one forever turned away. In this stillness, there's a kind of symmetry, a cosmic reflection of partnership. Earth pulls on the moon, and the moon pulls on Earth. The same gravitational tides that froze the moon's rotation still act on our oceans. They lift and lower the seas twice each day. They move continents by imperceptible degrees. Over vast spans of time, those tides have also slowed Earth's own rotation, lengthening our days from what was once just a few hours to the 24 we know now. The process continues almost immeasurably slow, but constant. Millions of years from now, Earth, too, might become tidally locked to the moon, each showing only one face to the other. The two bodies would turn together in perfect synchrony, eternally bound. But long before that, the sun will change everything, and this delicate balance will vanish into the wider motions of the solar system. Still, the present harmony holds one rotation for one revolution, a relationship maintained by the faint tug of every molecule and mountain. Let yourself picture that orbit now. You drift silently above the Earth-Moon system far enough away that both appear suspended in a single frame of dark. The Earth glows blue and white. The Moon gleams in silver gray. Between them, gravity stretches an invisible bridge, a tide of motion, a thread of pull and return. The Moon turns slowly, showing the same face to the planet it circles. You can see the far side now, the one that never looks back. It is cratered, ancient, scarred by time. The surface rises and falls like frozen waves of stone. You watch as the Terminator line, the boundary between light and dark, slides across its peaks. Shadows stretch for hundreds of kilometers, then recede again. There is no air, no wind to shape the dust. Every crater remains preserved since its impact. On this hidden side, the story of the early solar system lies unblurred, undisturbed by erosion or weather. Tidal locking kept it safe, an untouched archive of cosmic history sealed behind the Moon's steady rotation. And yet the far side's isolation posed a challenge. No radio signals from Earth could reach it. When Apollo spacecraft later orbited behind the Moon, communication fell silent for minutes at a time. Astronauts described the experience as eerie, absolute radio darkness, a separation so complete that even the voices of mission control disappeared. For scientists on Earth, this blackout symbolized something profound, the limits of observation. Until the 1950s, the far side was the great unseen landscape of the inner solar system. Its existence known, its nature unknown. A perfect example of how motion and gravity can hide a world in plain sight. But gravity hides nothing forever. Curiosity, persistence, and a spark of human invention would change that. The understanding of tidal locking did not come all at once. In the 17th century, astronomers like Giovanni Cassini observed the same lunar markings over time and began to realize the Moon must be turning at a rate equal to its orbit. Isaac Newton's laws of motion and gravitation later provided the framework to explain why. The mathematics of tides. How gravitational gradients stretch and slow rotating bodies became a window into planetary evolution. The concept applies far beyond our Moon. Mercury, for instance, is locked in a 3-2 resonance with the Sun. It spins 3 times for every 2 orbits. Many moons of Jupiter and Saturn are tidally locked to their planets, always showing the same face. Even exoplanets orbiting close to their stars are likely to experience the same fate. Some worlds may forever face daylight on one hemisphere and eternal night on the other. Tidal locking is not rare. It is the quiet conclusion of cosmic intimacy, the end point of gravitational companionship. When we speak of the moon's dark side, it is a misnomer. The far side receives just as much sunlight as the near side. It's not dark, but unseen. Half a lunar day, about 2 Earth weeks, is spent in daylight and half in night. The difference lies not in illumination, but in relationship. The far side is lit by the sun, not by the earth. Its nights are deeper, its horizons more absolute, because no reflected earth light softens them. If you stood there at lunar noon, the sun would blaze unfiltered in a black sky. If you stood there at midnight, the stars would be unblinking, undisturbed by atmosphere or haze. It would be the most silent night imaginable, a silence so complete you might feel sound itself had never existed. This balanced light and dark, seen and unseen, connects to how the moon itself formed. Billions of years ago, a Mars-sized body likely collided with the early Earth. The impact tore free immense amounts of material which coalesced into our moon. In the molten aftermath, gravity reshaped both worlds. As the moon cooled, the heavier elements sank toward its core. The near side remained thinner and warmer, leading to vast lava plains, the Maria. The far side cooled faster and developed a thicker crust, its volcanic activity stifled. Tidal locking preserved that asymmetry. The near side stayed oriented toward Earth, its crust flexed by gravitational stress, while the far side remained stable, heavier, and unchanging. The result, a moon with two faces, one smooth and familiar, one rugged and alien. Even now, the line between those hemispheres, the lunar terminator of our awareness, is as much emotional as physical. One face comforts us, the other beckons. In every age, the moon's hidden half has symbolized mystery, introspection, and the unknown. To lie under the night sky and wonder what lies beyond the visible is to feel in miniature the same curiosity that drives exploration itself. The unseen side of the moon is the unseen side of ourselves, the part that turns inward, away from the brightness quietly holding its own history. As you rest beneath the same sky, the moon is out there now, turning through its orbit so slow, so precise, that the face you see will still be the same tomorrow, and the next night, and the next 1,000 years. But behind that familiar glow, the far side continues to drift unseen through the dark, a hemisphere of silence. Soon we'll leave the timeless stillness of tidal locking and step into movement again, the era when humanity first reached beyond the pull of Earth, when rockets and radar and radio finally revealed what no telescope ever could. The age when myth gave way to metal and light, when the unseen became seen. The moon has turned this way for billions of years. Tidal locking holds its rhythm steady, a quiet duet between gravity and time. For as long as humans looked up, we saw only one side, the same pattern of light and dark. The far side waited patient, unseen. It carried its craters through millennia of moonrise turning in silence, while myths and mathematics tried to imagine its face. And then not so long ago we began to reach upward. Our machines of metal and fuel learned to rise through the air and cross the night. What had been the subject of wonder became a destination. The stillness of the moon would meet the fire of rockets. And from that meeting, the unseen hemisphere would finally be revealed. For thousands of years before the first launch, humanity's relationship with the moon was made of stories. It lit our calendars, our poetry, our sense of rhythm and return. Its changing phases guided harvests, inspired symbols of rebirth and reflection. But its nature, its substance, its surface, was the subject of deeper curiosity. The philosophers of ancient Greece were among the first to ask questions that echoed toward spaceflight. Anaxagoras suggested that the moon was a rocky world, lit not by its own fire, but by reflected sunlight. He imagined mountains and valleys long before telescopes could confirm them. Aristotle, cautious but curious, wrote of celestial spheres, crystalline shells holding the heavens in place. Even then, there was tension between myth and observation, between the luminous ideal and the physical reality. As centuries passed, the moon's mystery grew only more beautiful. In the Middle Ages, poets imagined its far side as paradise or purgatory. Alchemists thought it might be a mirror realm where the elements themselves were reversed light for dark heat, for cold truth, for dream. Each myth, in its way, was a reflection of longing. The hidden hemisphere became a canvas for the unseen. Then in the 17th century, telescopes changed everything. Galileo Galilei lifted his lens toward the moon and saw it not as a perfect orb, but as a world. He sketched shadows across crater rims, jagged mountains catching the dawn. The moon was revealed as a landscape, imperfect, solid, ancient. But even with this clarity, one mystery endured the unseen side. No matter how powerful his telescope, Galileo could not turn the moon to face him. The far side remained a blank circle in every lunar atlas, a region of imagination left unmarked. By the 19th century, a new kind of exploration began in the pages of novels. Writers like Jules Verne and H.G. Wells gave the moon new life. Verne's From the Earth to the Moon envisioned a giant cannon in Florida launching men toward lunar orbit. Wells, in The First Men in the Moon, imagined strange creatures living in its caverns, societies adapted to the long lunar night. Their stories were speculation, but their tone had changed, no longer reverence from afar, but ambition. Humanity was beginning to see travel beyond Earth as something imaginable, perhaps inevitable. Beneath those dreams, science was catching up. In laboratories and observatories, early physicists studied the motions of planets, the chemistry of stars, the faint pull of gravity, and somewhere between theory and imagination, the first equations of spaceflight began to appear. In Russia, a school teacher named Konstantin Tsiolkovsky dreamed beyond the horizon. In 1903, he published his Exploration of Cosmic Space by Means of Reaction Devices, a work that contained the essence of every rocket that would ever fly. He wrote of multi-stage rockets, liquid fuels, and the mathematics of escape velocity. He derived the rocket equation showing how speed increases logarithmically with expelled mass. In words both technical and poetic, he declared, "Earth is the cradle of humanity, but one cannot live in the cradle forever." His thoughts were not blueprints yet, but philosophy mathematics written in wonder. Still, they provided the architecture of possibility. In the United States, Robert Goddard turned theory into practice. In 1926, he launched the first liquid-fueled rocket from a snowy field in Massachusetts. It rose only 12 meters, but it was enough. In its smoke and spark lay the first whisper of future trajectories of lunar orbiters, of astronauts, of the quiet photographs that would someday return from the far side. In Germany, Hermann Oberth carried the same vision forward. His book, The Rocket into Planetary Space, laid the physics of interplanetary flight. Among his readers was a young engineer named Wernher von Braun, who would later transform these theories into engines capable of piercing the edge of Earth's gravity. Across continents, a pattern was forming. Dream, then mathematics. Mathematics, then machinery. Machinery, then motion. Not all beginnings are gentle. The same science that promised exploration first became a weapon. During the Second World War, German engineers developed the V-2 rocket, the first object built by humans to reach the edge of space. It rose above the atmosphere, curved through the stratosphere, and fell again in destruction. The technology was born of conflict, but the achievement was undeniable. For the first time, a machine of Earth had touched the black above the sky. When the war ended, that knowledge scattered across nations. The scientists of both sides, engineers of extraordinary skill, were taken to new lands. Von Braun and his team went to America. Others began work in the Soviet Union. The same mathematics of propulsion would now serve a different cause, not conquest, but discovery. Then came a small sphere of polished metal, no larger than a beach ball. In 1957, the Soviet Union launched Sputnik 1. It beeped softly as it orbited Earth, sending radio pulses through the night. The sound was simple, an electronic heartbeat, but it carried profound meaning. Humanity had left the planet. The cradle was opening. 1 year later, in 1958, the United States responded by creating a new agency, NASA, the National Aeronautics and Space Administration. Its purpose was not merely competition, but curiosity to study, to explore, to send instruments, and eventually people beyond the sky. Between the Soviet and American programs, a new kind of race began. It was not the frantic dash of athletes, but the deliberate climb of engineers and scientists, each step built on careful precision. Every launch was a question. Every signal from orbit was an answer. The moon, as always, waited, visible, steady, and half unknown. Its far side, untouched by eyes, untouched by radio, became both target and mystery. In October 1959, a Soviet spacecraft named Luna 3 rose beyond Earth's pull and swung around the moon. Its mission was simple yet profound: to take photographs of the hemisphere that never faces us. For the first time, humankind looked upon the far side directly. The images were blurry, ghost-like, filled with contrast and grain. But they showed a world utterly unlike the one we knew. Where the near side had wide, smooth plains, the far side was a maze of craters, dense, rugged, ancient. The Maria, the dark seas that shaped the moon's familiar face, were nearly absent. Astronomers were astonished. The far side's crust seemed thicker, its surface older. Something in its formation had made it asymmetrical, a record of the moon's own early history, preserved by the constancy of tidal locking. Those first photographs were more than data. They were a mirror of human desire to see the hidden, to reach the unreachable. The far side had finally stepped from myth into fact. Once Luna 3 returned its pictures, the world's gaze sharpened. If the far side was real, it could be mapped. If it could be mapped, it could be known. Over the next decade, both nations sent wave after wave of spacecraft robotic emissaries that turned silent arcs around the moon. NASA's Ranger probes from 1961 to 1965 flew straight toward the surface, taking photographs until the final instant before impact. Their brief lives produced thousands of images, close-up views, that proved the moon's terrain was solid and firm, not the powdery quicksand some had feared. Then came the surveyor missions. Between 1966 and 1968, they performed gentle landings, extending mechanical arms into lunar soil. They tested its texture, its composition, its ability to bear weight. Those findings would later give engineers the confidence to send humans to stand there. Orbiting above, the lunar orbiter missions mapped both hemispheres with high precision. The photographs from those orbiters became the blueprint for the Apollo landings. Each crater, each ridge, each plane was catalogued. Even in black and white, the moon's hidden geography began to emerge in exquisite detail. Each of those early spacecraft had a kind of grace. They were built not for beauty, yet they carried it. Silver bodies gleaming in the void, antennae unfolding like metallic petals, cameras blinking in the sunlight of space. They traveled without sound, without life, but with intention, the distilled intelligence of thousands of people on Earth. From mission control, scientists watched lines of data crawl across glowing screens. A few minutes of radio delay separated question and answer, but in that interval was wonder. Every photograph received was a fragment of reality returned from the unseen side of the sky. The far side was no longer mythic darkness. It was terrain, charted, measurable, yet still serene in its silence. When Apollo 8 reached lunar orbit in December 1968, humans saw the far side with their own eyes for the first time. Astronauts Frank Borman, James Lovell, and William Anders watched as the surface rolled beneath them endless craters and shadowed ridges. Anders called it a stark, battered, desolate place. The radio went silent as their capsule slipped behind the moon, cutting them off completely from Earth for long minutes. Imagine that silence. No signal, no sound, only the hum of instruments and the slow heartbeat of the spacecraft. Outside the window, a landscape older than continents drifted past. Each orbit they emerged again into sunlight, and Earthrise appeared a blue marble lifting over a gray horizon. For the first time, humanity saw its own home as a world apart, small and luminous. The far side of the moon had given us not only new knowledge, but a new perspective of ourselves. Every step that led to that moment, the equations, the engines, the photographs, was part of a larger pattern, the shift from imagination to experience. The far side had once been a dream painted in myth and speculation. Now, it was geography, geology, physics. Its mountains had names, its basins, coordinates. It was no longer unreachable. Yet even as we mapped and measured, something remained unchanged, the quiet of that hidden hemisphere. No atmosphere, no wind, no life to erode the record of creation. Every crater still tells the story of an impact billions of years old. Every ridge still carries the tension of tides and time. In a way, the moon's far side reminds us of our own beginnings. We too emerged from collision and gravity, from heat and dust. We too are shaped by forces we cannot see, but can feel the pull of curiosity, the slow locking of imagination to reality. The age of myth never truly ended. It simply evolved. We no longer tell stories of spirits living on the moon. We send machines, and they tell the stories for us through photographs, through seismic data, through the glow of reflected sunlight in their sensors. Each transmission a new kind of myth, one measured in wavelengths, translated by mathematics, but still born from wonder. Even now, as robotic orbiters continue to circle the moon, the line between poetry and science remains soft. A probe sending data through the dark is both an act of measurement and of faith, a belief that something hidden can be known. And from that belief, the path continues. From Luna 3 to lunar orbiter. From Apollo to Artemis. From myth to reality, and from reality to meaning. As we leave this chapter of first discoveries, the moon still turns in silence. The far side faces outward toward the rest of space, unblinking and unobserved by any natural eye. But we know it now. We have seen its scars, traced its craters, felt its silence through the voices of those who orbited it. In the next part of our journey, we'll drift closer still to the first machines that landed the astronauts who followed, and the moments when the far side stillness became not just a mystery, but a place of understanding. The far side of the moon had waited since the beginning of time, patient as stone, unseen by every creature that ever looked up. Then, for the first time in human history, machines made of wire and metal and hope began to move toward it. The age of imagination had given way to the age of motion. The silent face that turned away for billions of years was about to meet the gaze of Earth. Even now it feels astonishing how quickly the invisible became visible once we found the courage to leave home. Only 12 years passed between the first liquid-fueled rocket's small arc above a frozen field and the first camera that saw the moon's hidden side. A blink in cosmic time. Yet everything changed. Let's drift there slowly through that era of trial and light. Through the first missions that bridged the distance between myth and measurement. It began with a hum over Moscow radio frequencies. On October 7, 1959, the Soviet spacecraft, Luna 3, sent back a faint signal. Waves of static carrying images across nearly 400,000 kilometers of emptiness. The spacecraft itself was small, barely over a meter and a half long, weighing less than a family car. It carried film cameras, a transmitter, and a hope that its journey would work. After circling the moon in a looping path, Luna 3 turned its lens toward the unseen hemisphere and began to photograph. Each exposure was automatic, timed by sunlight, framed by uncertainty. The pictures returned to Earth days later were grainy, imperfect, ghost-like, yet they were among the most profound images ever captured. For the first time, humanity saw the far side of the moon. The surface was nothing like the one we knew. Where the near side displayed wide, dark plains, the Maria, the far side, was rough and pale, covered almost entirely with craters. The few dark spots visible were small and isolated. One later named Mare Moscoviense became famous for its rarity, an island of basalt in a sea of ancient highlands. Scientists immediately noticed something extraordinary. The far side appeared to have a thicker crust. Its density of craters suggested extreme age. Perhaps the near side's thinner crust had allowed volcanic flows to flood its basins long ago, while the far side had sealed itself early, preserving a record of the moon's first billion years. Those fuzzy photographs carried meaning beyond geology. They turned mystery into map, and they marked the beginning of a slow, luminous unveiling. Once Luna 3's transmissions faded, the world turned its antennas back toward the moon. The Cold War's tension had made space a theater of competition. But behind that rivalry was a shared wonder. In the early 1960s, both the Soviet Union and the United States sent new probes, each carrying sharper cameras, better transmitters, and hearts of circuitry. Their names, Ranger, Surveyor, Lunar Orbiter, sounded technical, but their journeys were deeply human. Each mission was, in essence, a question sent into silence. What is the moon made of? Could we land there? Could we return? Between 1961 and 1965, NASA launched a series of 9 spacecraft under the Ranger program. Their purpose was direct to impact the moon while photographing every moment of descent. For years, these missions failed mechanical faults, missed trajectories, radio silence. But in failure, scientists learned. Each misstep refined the next attempt, like a sculptor chipping away until form emerged. Finally, Ranger 7, launched in 1964, succeeded. It returned over 4,000 high-resolution images before crashing onto the lunar surface. The images showed a terrain solid and stable with defined rocks and shadows. There was no soft powder waiting to swallow spacecraft as some had feared. The moon was real ground. The final Rangers 8 and 9 continued that success. Their final transmissions came seconds before impact images of craters and plains flashing across monitors on Earth. It was a strange ritual of discovery through destruction, each mission sacrificing itself for a few more moments of clarity. After the Rangers proved the surface was safe, NASA sought to touch it. The Surveyor program, 1966-1968, was designed for soft landings, something never before achieved. The spacecraft were delicate machines with tripod legs, cameras, and instruments to scoop and test lunar soil. Surveyor 1 descended in June 1966, firing retro rockets as it approached. For a few tense moments, the world waited in radio silence. Then came a steady signal touchdown confirmed. For the first time, a spacecraft had landed softly on another world. Surveyor's camera turned, capturing its own shadow stretching over alien dust. The images revealed grains of basaltic sand, small rocks, and a smooth horizon under a black sky. Later, missions tested soil mechanics, fired thrusters to see how dust behaved, and even carried small shovels to measure depth and firmness. What they found changed everything. The soil called regolith was loose but cohesive, able to support the weight of future landers and humans. The moon was no longer a mystery of possibility. It was a destination with texture and touch. As Surveyor explored the surface, a new fleet of spacecraft began to orbit above. Between 1966 and 1967, 5 lunar orbiters mapped the moon in detail never before imagined. Their task was to scout potential landing sites for the upcoming Apollo missions, but their contribution went far beyond logistics. Using onboard film cameras, they photographed the moon from altitudes as low as 60 kilometers, developing the film in orbit, scanning it with light beams, and transmitting the images line by line back to Earth. Each picture was a digital dawn, an analog ghost reborn as electronic data. The Lunar Orbiter program produced over 2,000 images covering nearly the entire surface, including the far side. The photographs revealed not only geological complexity, but unexpected grace reels winding through plains rays stretching from impact craters like frozen lightning. For the first time, the far side could be studied in context with scale coordinates and light. It became a landscape, not a rumor. While NASA mapped and landed, the Soviet program continued to reach for new milestones. After Luna 3's success, later missions refined the craft and its cameras. Luna 9 in 1966 achieved the world's first soft landing, sending panoramic photos of scattered rocks and gentle slopes. Luna 13 followed with seismic experiments, measuring how shock waves moved through the lunar ground. The Zond program tested re-entry capsules designed to bring living beings, first animals, then humans, around the moon and safely back to Earth. Though human crews never flew aboard Zond, its circumlunar paths demonstrated that orbit and return were possible. The far side remained a scientific treasure, but its exploration now carried the momentum of progress. Humanity had learned to cross space orbit a world and land with precision. Each mission built upon the silent knowledge of the one before it. With images now covering nearly the entire lunar surface, scientists began to notice striking differences between hemispheres. The far side's crust, measured by later gravimetric studies, is up to 20 kilometers thicker than the near sides. Its composition shows fewer basaltic flows, meaning it cooled faster sealing volcanic channels that once spewed lava on the Earth-facing side. The most remarkable feature of all is the South Pole Aitken Basin, a vast depression over 500 kilometers wide and 13 kilometers deep, the largest impact structure in the solar system. This immense scar lies mostly on the far side, and its formation may have exposed material from the moon's mantle. Though not yet fully explored during the early missions, hints of the basin's enormity were already appearing in lunar orbiter photographs. Its circular outline and shadowed depths suggested an event of unimaginable force, an asteroid strike that reshaped half a world. The far side, once unseen, had become a record of cataclysm, each crater a moment of impact frozen forever untouched by atmosphere or rain. Every spacecraft that passed behind the moon encountered a brief moment of absence. No matter how advanced the transmitters or antennas, radio waves cannot pass through the lunar body. When a probe, or later a human spacecraft, slipped behind that solid sphere, communication ceased completely. This blackout became a signature of lunar exploration, a predictable void in every orbit. For mission controllers, it was a period of stillness, a pause where machines drifted beyond hearing. For astronauts, it was something deeper isolation in its purest form. When Apollo astronauts later described this blackout, they used words that sounded like poetry. Michael Collins called it a kind of comfortable loneliness. Frank Borman said it felt like falling through absolute quiet. The far side, invisible and unreachable, had not only geographical silence, but electronic silence, a brief return to the ancient stillness that existed before radio, before flight, before thought. By the late 1960s, the moon was no longer mysterious in the way it once was, but it was still profoundly beautiful. Every mission taught something new. Ranger showed us that the surface was firm. Surveyor proved that we could land. Lunar Orbiter revealed the detailed geography. And Luna 3 had given us the first glimpse of the unseen. Together, these missions built a bridge, one of knowledge rather than stone, linking human imagination to reality. The far side's craters received names Tsiolkovsky, Jules Verne Korolev. The act of naming itself felt sacred, a way of saying, "We see you now." When you think of those missions now, decades later, imagine them not as mechanical feats, but as lights moving slowly through the dark. Tiny arcs of purpose crossing the infinite. each mission carried within it the pulse of every human who ever looked up at the moon and wondered. In their successes and failures, they formed a quiet rhythm. Launch silence, discovery return. Like breathing, but on a planetary scale. And through that rhythm, humanity learned to see differently. Not only outward toward the moon, but inward toward its own capacity for patience and precision, for daring and curiosity. The far side of the moon, once a symbol of eternal mystery, became a place where human reason met its reflection, not conquered but understood. But now, as the 1960s deepened, that understanding reached its most intimate form. After years of mechanical eyes and coded signals, the next step was inevitable. The far side would soon be seen not by cameras alone, but by human eyes, unfiltered, unmediated, alive. The explorers of Apollo would orbit the moon themselves, watch the Earth vanish behind it, and describe what it felt like to be the first living beings to witness both sides of another world. And in their words, the silence of the far side would find its human echo. The moon had been mapped, measured, and touched by machines. Yet something remained incomplete, an emptiness between image and experience. For all the thousands of photographs and streams of telemetry, no human eye had yet looked down upon the far side directly. No heartbeat had pulsed through that deep silence, unshielded by atmosphere or distance. Now came the next step in the long unfolding, humans themselves crossing the void between Earth and moon, becoming part of the celestial rhythm they once only observed. The far side was waiting, still patient as ever. And for the first time, it would be seen not only by metal and glass, but by living eyes filled with wonder. It was December 1968 when Apollo 8 left Earth's gravity behind. 3 men, Frank Borman, James Lovell, and William Anders, became the first to travel beyond the gravitational cradle that had held all life since the beginning. Their mission to orbit the moon, to test the path that later missions would take to the surface, and to see what no one had ever seen. As the spacecraft approached its target, radio voices echoed through mission control in Houston. A blue world shrank behind them. Ahead, the gray sphere of the moon grew until it filled every window. Then came the moment that could never happen from Earth. The far side rose into view. Anders described it in a whisper of words that still carries across time. It's a vast, bleak, forbidding expanse of nothing. A landscape so ancient it felt beyond change, beyond time itself. The surface stretched in every direction, cratered and scarred. Shadows pooled in valleys untouched by light. The astronauts traced names over new features: Tsiolkovsky, Korolev, Mare, Moscoviense, and felt perhaps what the first sailors felt when they glimpsed a new shore. But unlike those sailors, they could not land. Their orbit was brief, precise, rehearsed. Still, as they swung behind the moon radio, contact with Earth vanished. For 20 minutes, each orbit, they were alone, completely alone. No signal, no guidance, no sound but the quiet hum of their spacecraft and the slow beat of their own hearts. The far side was a wall between them and everything they had ever known. When they emerged again into sunlight and regained communication, they carried with them a new understanding of silence. On their 4th orbit, Anders looked out the window and saw something unexpected. As Apollo 8 came around the far side, the Earth rose above the lunar horizon, a delicate blue sphere floating above gray plains. He lifted a camera almost without thinking and captured one of the most famous images in human history, Earthrise. It showed the smallness of our world, the fragility of its colors. Clouds like breath, oceans like veins, continents like shadows of ancient fire. In that photograph, the far side of the moon became the frame, and Earth became the jewel within it. The image reshaped how humanity thought of itself. From that moment on, exploration no longer meant escape, it meant perspective. The moon's hidden hemisphere had given us a new way to see home. A few months later, in May 1969, Apollo 10 retraced the same path. This mission was a test flight for the first landing attempt, descending close to the lunar surface before returning to orbit. Astronauts Thomas Stafford, John Young, and Eugene Cernan again crossed into radio darkness as they looped behind the moon. Each pass revealed new details, crater chains, fault lines, shimmering slopes near the limb. They marveled at the brightness of the sunlight on lunar dust so intense it seemed like glass. Cernan described the far side as a picture in gray. No air, no color, no haze, just pure light and shadow. Their mapping cameras documented the terrain with precision. The data they brought back helped choose landing sites for the next mission. But beyond navigation, the astronauts spoke of something emotional, an awe that no photograph could capture. When they reappeared from behind the moon and heard Earth's voice again, there was relief, yes, but also a strange longing. For those 20 minutes of silence, they had been the only humans in existence to see that half of the lunar world directly to exist in a place where Earth was absent. Then came Apollo 11, the mission that landed humanity on the moon. But while Neil Armstrong and Buzz Aldrin descended to the surface, Michael Collins remained alone in orbit aboard the command module Columbia. As the spacecraft passed behind the moon, he entered that same familiar silence. Radio blackout, total isolation. But this time, he was completely alone. No crew to speak to, no Earth to hear from, no sound at all, but his own breathing. He described the experience later with calm precision. "I am alone now, truly alone, and absolutely isolated from any known life. I am it." Yet Collins did not speak of fear. Instead, he called it peaceful. The far side felt serene, unchanging, indifferent to time or presence. Outside his window, the moon glowed softly gray and endless. Beneath him, past craters billions of years old, the frozen scars of cosmic collisions. He orbited in silence, watching as sunlight traced the contours of mountain rims. Each pass revealed the far side anew, a place both alien and strangely intimate. When he re-emerged from behind the moon, Earth's voice flooded his headset again, and the circuit was complete. Human presence had encircled another world. After Apollo 11's triumph, 5 more missions followed, each expanding knowledge of both sides of the moon. Though the landings took place on the near side, every mission orbited through the far side's shadow. Astronauts described it in similar words: bleak, majestic, eternal. Alan Bean said it looked like a battlefield from which the armies had gone. John Young compared it to a cemetery of stone. From those orbits came hundreds of photographs, radar readings, and gravitational data. The far side's crustal thickness, magnetic anomalies, and density variations began to reveal the moon's internal structure. Scientists discovered a curious feature. Certain regions of the far side emit unusually strong magnetic signals, remnants of an early lunar dynamo. Though the moon no longer has an active magnetic field, patches of magnetized rock hint at a time when its core was molten and alive. Other measurements confirmed the asymmetry first glimpsed by Luna 3. The far side's crust is thicker, its maria fewer, its highlands taller. These differences speak of ancient tidal forces and unequal cooling, a geological story written in shadow. To the astronauts, the scientific data was vital, but the emotional experience was deeper still. In those quiet minutes behind the moon, they felt the complete absence of the familiar world. Imagine it. You float in a small capsule the size of a car with a thin shell of metal between you and the vacuum. Outside the window stretches an endless field of gray stone curving away into darkness. Behind that stone, unseen, lies Earth, a glowing world you cannot reach or hear. You are between worlds, inside silence itself. A silence not empty, but full-filled with age, with gravity, with the soundless hum of the universe. Astronauts described it as humbling, even sacred. They realized that exploration is not only about discovery, but about returning to Earth, to self, to perspective. The far side became a mirror showing how small and fragile humanity truly is. From the photographs taken during Apollo missions, scientists created the first comprehensive lunar maps, topographic charts showing every mountain, plain, and crater in measured relief. The far side revealed structures of breathtaking scale. The South Pole. Aitken Basin, deeper than Mount Everest, is tall. Tsiolkovsky Crater, with its central peak catching sunlight like glass. Networks of smaller basins overlapping like ripples in frozen water. Apollo's orbital sensors also detected mass concentrations, or mascons, regions of stronger gravity beneath large basins. These were likely caused by dense basaltic material pooled in ancient impact sites. On the far side, where the crust was thicker, such features were fewer but still striking. Through these maps, scientists began to reconstruct the moon's earliest history. They saw evidence of the late heavy bombardment, a period about 4 billion years ago, when countless asteroids struck the young worlds of the solar system. The far side's untouched surface preserves that record, a fossil of impact and endurance. Even with all the data, the far side retains an atmosphere of mystery, not the mystery of ignorance, but of perspective. For the astronauts who saw it, the far side was not frightening, only distant. It reminded them of time itself, slow, enduring, impartial. The craters were older than continents. The dust had lain unmoved for eons. One can imagine them looking out the window, watching the horizon drift past, feeling both awe and calm. Perhaps they realized that the universe does not rush. It unfolds at a pace beyond our impatience. The far side is a lesson in stillness. It is what happens when a world turns without interruption for billions of years, unvisited by wind or rain, unbothered by life. Every grain of dust is a chronicle of light and gravity. To gaze upon it is to see endurance itself, stone holding memory. When Apollo 17 departed the moon in December 1972, the human era of lunar exploration paused. No person has since orbited the far side. No eye has seen that hidden landscape directly in half a century. Yet it remains there unchanged, as though waiting for our return. In its craters and basins, our past journeys are reflected the courage, the precision, the quiet awe of the first explorers. Every spacecraft that passes today, robotic or crewless, still slips through that same shadow. The silence remains the same. The radio still fades. The ancient balance between Earth and Moon still holds. The Apollo missions revealed what was hidden, but they also taught something deeper, that discovery and solitude often walk together. When the Apollo crews returned to Earth, they brought back more than samples and data. They brought back perspective. The far side had shown them a world without sound or color, without change or decay. In that starkness, they saw beauty. They saw the purity of geological time, the calmness of creation that needs no observer to be complete. Frank Borman later said, "The moon is a magnificent desolation." The phrase carries both awe and humility, a realization that beauty does not depend on warmth, and that emptiness is not the same as absence. The far side in its silence reminded them that the universe is not built for us, yet it allows us to witness it. That witnessing is its own purpose, its own quiet triumph. Now the moon continues its steady turn, one face forever toward us, one forever away. But the boundary between known and unknown is softer than before. Through human eyes we have crossed it once, and that crossing remains within us. The far side no longer belongs to myth. It belongs to memory, to those moments when living beings drifted behind a world and saw the universe without the light of Earth. And yet the story continues. Beyond human vision, satellites and instruments keep watching, listening, measuring. New missions wait on launch pads preparing to return to that silent hemisphere. The far side is not finished with us. It is still a page of the universe slowly turning toward the light. The far side, seen by human eyes and machines alike, told a story of silence and endurance. Yet beneath its quiet surface, deeper patterns waited to be understood. Traces of impacts so vast, they reshaped the moon itself. Among these, one stood apart immense beyond measure. The South Pole Aitken Basin, ancient and solemn, lies across the southern hemisphere of the far side. Its existence is a scar older than continents, older than the seas of Earth. It is not merely a crater, but an event, one of the greatest in the solar system's history. In its shadows, we glimpse both violence and creation, the twin forces that built the worlds. Stretching to 500 kilometers from rim to rim, the South Pole Aitken Basin covers nearly a quarter of the lunar surface. Its depth, measured in later centuries by orbiters and altimeters, reaches 13 kilometers at its lowest point, deeper than any canyon, wider than any ocean trench on Earth. To the naked eye, it is not easily seen, for it lies on the moon's hidden side, spanning from the southern pole northward to the crater Aitken. But from orbit, its outline forms a massive ellipse, smooth and shadowed, a depression surrounded by jagged highlands. It is the oldest and largest known impact basin on the moon, and perhaps in the entire inner solar system. A fossil of catastrophe. A wound from the solar system's youth. When a colossal asteroid struck the moon billions of years ago, molten rock surged outward. The shock waves penetrated deep, perhaps even to the mantle. The crust cracked, melted, and froze again. The result was not just destruction, it was revelation. Within that basin, the moon's deeper layers were lifted and spread outward, exposing materials unseen elsewhere. Scientists believe that what lies at its core may be the moon's mantle itself, a layer normally hidden beneath 20 to 50 kilometers of crust. The impact was not an end. It was a beginning of understanding. The first hints of the basin appeared in the lunar orbiter photographs of the 1960s. At the time, its full scale could not yet be appreciated. The far side's lighting was harsh and resolution was limited. Scientists noticed a vast lowland stretching near the southern limb ringed by rugged mountains. Some suspected an impact structure. Others thought it an illusion of perspective. Decades later, as technology improved, clarity came. The Clementine mission in 1994, a joint NASA Department of Defense project, mapped the entire moon in high-resolution digital imagery. Clementine's data revealed unmistakable curvature consistent with a single massive impact. Then, in 1998, Lunar Prospector confirmed the basin's full scale. Its instruments measured variations in gravity, showing a massive deficit where crustal material had been displaced by the strike. For the first time, humanity could see the outline not as a photograph, but as a field of force. The South Pole Aitken Basin had emerged from obscurity, recognized as a structure so immense it could hold the state of Texas and still have room for oceans. To understand the basin is to travel backward to the time when the solar system itself was young and violent. Roughly 4 billion years ago, during a period called the Late Heavy Bombardment, planets and moons were still sweeping through a debris-filled orbit around the newborn sun. Asteroids collided often. Craters marked every solid surface. The moon, smaller and with little atmosphere, recorded those impacts permanently. The South Pole Aitken event likely occurred near the end of that era. The object that struck may have been 50 to 100 kilometers wide, traveling at over 15 kilometers per second. In an instant, energy equivalent to billions of megatons was released, melting rock, vaporizing stone, sending shock waves that rippled through the moon's entire body. And then, slowly, everything cooled. The molten surface solidified. The crater filled with breccia and basalt. The atmosphere that briefly formed was lost to space. In the stillness that followed, time resumed its patient pace. Dust settled over melted plains. Smaller craters gathered on top layer upon layer of later impacts. Today, what we see from orbit is not an explosion, but its memory. Gentle ridges, smooth valleys, mineral traces beneath the regolith. The violence is gone. Only the form remains. Modern instruments reveal that the basin differs not only in shape, but in substance. Spectral analysis from Clementine, Kaguya, and Lunar Reconnaissance Orbiter LRO shows unusual mineral patterns, pyroxenes rich in iron, low-calcium rocks, and traces of thorium and potassium elements that suggest exposure of deep mantle material. If these readings are accurate, the basin may be the only place on the moon where we can study the composition of its inner layers directly. For geologists, it is a treasure, an open cross-section of a planetary body, a chance to read the pages of lunar evolution. The near sides Maria tell one-story volcanism, thin crust heat. The far sides highlands tell another ancient impact's thick crust endurance. But the South Pole Aitken Basin tells both. It connects them like a bridge between the moon's two hemispheres and two epochs. Its rim mountains, Leibniz Mandelstam. Aitken rise like fossilized waves marking where molten rock once surged. Inside the basin, craters such as Apollo and Planck lie within older scars stacked like reflections in water. Even its floor glows faintly different under sunlight, darker, denser, subtly metallic. A quiet echo of the world beneath. Near the basin's southern edge, the lunar surface tilts toward the pole where sunlight strikes at the shallowest angles. There, within craters that have not seen daylight for billions of years, instruments detected something unexpected: water ice. Radar and spectrometry data from Lunar Prospector and later the LRO revealed bright reflections in permanently shadowed regions, signatures of hydrogen likely bound in frozen form. This discovery transformed the moon's image once again. The far side, once thought dry and barren, holds hidden reservoirs of ice locked in perpetual darkness. These frozen patches are not lakes or sheets, but grains, tiny flecks mixed with regolith, preserved where the sun never reaches. They tell of ancient comets that may have struck and released their volatile cargo. Some molecules may even trace back to the earliest water in the solar system. In this way, the South Pole Aitken Basin is not only an archive of rock, it is a reservoir of memory, holding remnants of celestial collisions, perhaps the same water that now fills Earth's oceans and our own cells. Because of its immense scientific value, the basin has become one of NASA's most desired exploration sites. Robotic missions, such as China's Chang'e 4, which landed in 2019 within the von Karman crater inside the basin itself, have already begun this work. Chang'e 4 carried the Yutu-2 rover, which still roams across the gray soil, measuring minerals, studying surface temperatures, and listening for subsurface echoes. It confirmed what earlier missions hinted: the basin floor contains materials distinct from the highlands, likely remnants of the moon's lower crust or mantle. Future missions from NASA's Artemis program and international collaborators aim to return here, perhaps to drill beneath the surface to sample the oldest rocks to measure isotopes untouched since the dawn of planetary formation. For scientists, the South Pole Aitken Basin is a window into both the moon's interior and the early solar system's chaos. For dreamers, it is a destination half-shadowed, remote, and beautiful. When orbiters map the basin today, they use laser altimeters, pulses of light timed in billionths of a second. Each flash leaves Earth, strikes the moon, and returns across the void. From those echoes, we reconstruct mountains and valleys in exact detail. In a way, we are illuminating darkness with the gentlest of touches, light as measurement, light as understanding. The basin, once invisible, now exists in terabytes of data in glowing topographic maps, where color stands for height and shadow for depth. Red for ridge, blue for abyss. Every shade a translation of distance into meaning. Even as technology refines our view, there remains a quiet humility. No photograph, however precise, can capture what it feels like to imagine standing there under a sky without air at the bottom of a crater 2,000 kilometers wide, surrounded by walls that rise beyond the horizon. Above, the sun would hang low, glancing along the rim, lighting dust into silver flame. The stars would not twinkle, they would burn steady, and Earth would never rise. In that stillness, one might feel time itself, a gravity not of mass but of memory. The South Pole Aitken Basin also helps answer questions far beyond the moon. By studying its structure, scientists can infer how planets respond to colossal impacts. The pattern of fractures and crustal rebound provides clues about the mechanical strength of early planetary crusts. Comparing it to Mars's Hellas Basin, or Mercury's Caloris Basin, researchers see how similar events shaped every rocky world. In that comparison lies a broader truth, that creation and destruction are inseparable. Every planet is both a survivor and a scar. Some theories suggest that the Aitken impact may even have influenced the Moon's internal asymmetry. By excavating so deeply on one hemisphere, it could have shifted material inside, altering magnetic fields and volcanic activity. The near side's later eruptions may be in part echoes of that ancient collision. If so, the Moon's two faces are not merely opposite, they are consequences of the same event. The hidden and the familiar are born of the same strike. As we imagine future explorers returning to the basin, one can picture the scene: a small habitat on the rim, sunlight grazing its panels, antennas pointing toward relay satellites hanging high above the Moon's far side. From that vantage, astronauts would stand where no human has stood before, inside the largest impact basin ever known. They would see the rim stretching like a frozen tide, the horizon curving away in shadow. The ground beneath them would be older than the first ocean on Earth. They might collect samples rock melted when the impact struck glass beads forged in an instant of cosmic fire. They might analyze the dust and find traces of water ice preserved in perpetual night. And perhaps in quiet moments, they would simply look outward into darkness and feel what generations before them felt when they first glimpsed the Moon's far side, the mingled awe of vastness and belonging. For to stand on the far side is to stand at the edge of the known, facing outward to the universe. The South Pole Aitken Basin is more than geology. It is metaphor. It reminds us that impact and illumination are part of the same process, that every scar on a world or a heart reveals something once hidden beneath the surface. The Moon wears its history openly without weather to erase it. We too carry our histories, some visible, some buried deep. And like the basin, we are shaped by the collisions that formed us. When we study that immense hollow, we are studying endurance. Stone that absorbed unimaginable energy and still holds its form. Darkness that shelters traces of water of possibility. Even now, sunlight creeps along its rim each lunar day, touching peaks that rise 20 kilometers above the floor, casting shadows hundreds of kilometers long. The rhythm of light and dark continues unbroken since before life began on Earth. In that rhythm there is serenity. The story of the South Pole Aitken Basin is the story of revelation through patience. It waited unseen for billions of years. It was glimpsed, faintly understood, slowly mapped carefully, and finally embraced as a key to lunar and planetary history. And still, it waits for new explorers, new instruments, new eyes. For another generation to listen to the silence of the far side and hear within it the steady hum of cosmic time. The South Pole Aitken Basin lies in silence, vast and unreachable by ordinary means. To stand there, or even to communicate with a rover crawling across its surface, requires more than curiosity. It requires ingenuity, patience, and the quiet precision of engineering. Every orbit, every transmission, every landing on the Moon's far side is a test of distance and stillness. The far side is not simply a place. It is a silence, a wall between worlds. And to bridge that silence, we learn to speak through the void. On the near side of the Moon, communication is simple. A direct radio beam can reach Earth. Signals travel across space in just over 1 second, swift enough for command and response for the easy conversation of exploration. But on the far side, that connection is broken. The moon itself stands in the way, a solid wall of rock nearly 3,500 kilometers thick. No radio wave can pass through it. When a spacecraft slips behind the moon, it vanishes from Earth's sight. No radar echo, no telemetry, no whisper. For minutes or hours, it is as though it has ceased to exist. This blackout, inevitable, immutable, defines every mission that seeks to explore the far side. To send a lander there is to accept that it will never speak directly to Earth. Every message must find another path, another relay, another ear in orbit. It is a challenge born of geometry and gravity solved by patience and light. The first solution came with simplicity and grace: a relay satellite. Place a spacecraft high enough above the moon at just the right position, and it can see both the far side and the distant Earth. It becomes a bridge of light, catching signals from the hidden hemisphere and reflecting them back across space. In celestial mechanics, this point is called a Lagrange point, a place where gravity's forces balance so that an object may hover in near stillness relative to the moon and Earth. The ideal position for a far-side relay is Earth-Moon L2, about 65,000 kilometers above the moon's far side. From there, a satellite orbits in what's known as a halo orbit, a gentle loop that remains in view of both worlds. Like a translator between two speakers, it listens in one direction and whispers in another, constant, unbroken. When China's Chang'e 4 mission prepared to land on the far side, such a satellite Queqiao, meaning Magpie Bridge, was placed at L2. Its antennas unfolded like petals in the dark, forming the first permanent communication link to the unseen hemisphere. Now every photograph, every data packet from the Yutu-2 rover passes first through Queqiao's circuits before reaching Earth. A whisper across 100,000 kilometers of silence. The far side's environment is both calm and cruel. There is no atmosphere, no weather, no erosion, but also no protection. Temperature swings are immense. When sunlight strikes the surface, the ground can reach 120 degrees. When night falls, it drops to 180 degrees. A single lunar night lasts nearly 2 Earth weeks. For a machine, that long sleep is perilous. Circuits contract. Batteries freeze, lubricants solidify. To survive, engineers built resilience into silence. Spacecraft designed for the far side use radioisotope heater units, small pellets of plutonium dioxide that emit a steady warmth through their decay. This gentle heat, no larger than a handful of embers, keeps vital systems from freezing through the long lunar night. Power, too, is precious. Solar panels work beautifully during the 2 weeks of daylight, but during night they rest. Some landers enter hibernation, waking only when dawn returns. Others draw on batteries or radioisotope generators, their faint glow sustaining life where no light shines. The far side demands machines that breathe slowly, that wait, that endure. Each system must think in lunar rhythms: 2 weeks of light, 2 weeks of dark, forever repeating. To orbit the moon is one thing. To land softly on its unseen half is another entirely. Without direct contact, every maneuver must be pre-programmed, every descent autonomous. The lander cannot hear Earth's voice in real time. It must trust its own intelligence. This requires extraordinary precision. Navigation systems use laser altimeters, radar ranging, and star trackers to determine position with meter-level accuracy. Thrusters fire in controlled pulses, adjusting velocity in fractions of a second. When Chang'e 4 descended into the von Karman crater in 2019, its landing sequence was guided by cameras and onboard logic. It measured slopes, avoided boulders, and selected a flat region, all without command from Earth. Only after touching down did it send confirmation through Queqiao's relay. For mission controllers, those moments between descent and signal are timeless minutes of suspension when everything is unknown. The spacecraft is either alive or gone, success or silence, and there is nothing to do but wait. Yet, in those pauses lies trust, the quiet bond between creation and creator. We build these machines, send them away, and wait for their voices to return. The far side's terrain complicates not only communication, but travel itself. Its highlands are steep, its craters clustered, its dust fine and clinging. The regolith, though firm, can trap wheels and scatter light. Rovers must move with patience. Their cameras scan every rock, every ripple of dust, calculating safe paths. Their wheels turn slowly, avoiding sharp inclines and soft drifts. The Yutu-2 rover, still active years after its landing, moves just a few meters each lunar day. It stops often to rest, to charge, to measure. Each movement is deliberate, a gesture of endurance. Its instruments include ground-penetrating radar spectrometers and panoramic imagers. Together, they reveal layers of history beneath the surface strata of basalt and ejecta from ancient impacts. Even in movement, the rover becomes part of the stillness. It travels through time as much as space, reading the record of billions of years left untouched. Every engineering challenge solved on the far side becomes a lesson for future worlds. Relay satellites show us how to maintain communication across planetary shadows. Autonomous landing systems prepare us for Mars, Europa, and beyond. Thermal management teaches patience the art of surviving long nights without sunlight. These lessons converge in NASA's Artemis program, which plans not just visits, but presence outposts near the lunar poles stations orbiting in stable paths around the Moon. Such bases will rely on similar relays and networks, forming a web of communication around the Moon's entire body. Imagine it. A constellation of satellites circling in quiet choreography, linking far side to near side to Earth, Earth to the rest of space. The Moon becoming not a barrier, but a node, a whispering hub in the symphony of exploration. From those networks, the next generation of explorers will step outward to Mars, to the asteroids, to the deep dark where silence reigns. There is poetry even in the hum of transmitters, a pulse of radio waves traveling at the speed of light, crossing 300,000 kilometers of vacuum. Encoded in that pulse temperature readings, dust spectra, photographs, the rhythm of a rover's wheel. Each transmission is a heartbeat, faint but persistent. Each return signal a breath from another world. In mission control rooms, engineers watch those signals scroll across screens as streams of numbers, voltages, coordinates, bit rates. Yet within those numbers lies meaning, the echo of a landscape no human has seen, the whisper of a machine alive in shadow. Communication is not merely function. It is relationship. We build vessels that extend our senses across distance, and when they speak, we recognize something of ourselves in their voice. Despite all technology, contact remains fragile. Solar storms can disrupt transmissions, scattering radio waves across space. Micrometeorites can scar antennas or solar panels. A misaligned orbit can shift a relay's position, leaving moments of silence longer than intended. Every signal is a triumph against chance. Every photo received a small victory of persistence over emptiness. Engineers plan for redundancy, multiple transmitters overlapping orbits, protective shielding. They send commands in triplicate signals encoded with error correction so that even faint whispers can be reconstructed. There is tenderness in this precision, a kind of care expressed in equations and circuits. The care of a parent watching a child cross a great dark sea, trusting it will call home. Beyond survival and communication, there is another dream, one of listening rather than speaking. The far side, shielded from Earth's constant radio noise, is the quietest place in the inner solar system. No interference from transmitters, no chatter from satellites, no static from human technology. Only the cosmic background hum, the birth song of the universe itself. Astronomers dream of building a low-frequency radio observatory there, perhaps nestled within a crater's rim. It would listen to signals older than stars' radio waves from the universe's earliest moments, when the first atoms formed after the Big Bang. To build such an observatory would require all the engineering wisdom learned so far: relay networks, thermal control, autonomous construction. But the reward would be profound. Hearing the universe's first light in radio form sound, carried through time, echoing through the stillness of the far side. In that endeavor, engineering meets poetry again. Machines will listen where humans cannot, translating silence into knowledge. Engineering for the far side teaches a particular rhythm, the rhythm of patience. There are no quick results, no immediate feedback. Every command is sent across a gulf of seconds. Every answer takes time to return. To work in this way requires calm. It is a meditation of mathematics, a steady breathing through numbers and light. The engineers who guide these missions do not fight the void, they work with it. They know that silence is not failure, only delay. They wait and they listen. And when the signal returns, faint but clear, it carries a small miracle proof that our reach has crossed the dark and found itself again. From the first radio waves of Luna 3 to the constant link of Kwekiao, our communication with the far side has evolved from moments to continuity. Now we speak to the moon almost without pause. What was once impossible is now routine. What was once silence is now dialogue. And yet the mystery remains. Even as our instruments hum and our relays spin, the far side keeps its calm. No human voice echoes there. Only the whisper of machinery, the faint sigh of dust beneath robotic wheels. We listen across that stillness, not to conquer it, but to understand. Each improvement in technology brings us closer to hearing the universe as it truly is, quiet, balanced, endless. The South Pole Aitken Basin taught us the depth of time. Now engineering teaches us the delicacy of touch. Through invention, we have found ways to reach across shadow to bring light into silence without disturbing its peace. These solutions, antennas, relays, heaters. Thrusters are not just tools. They are acts of connection, expressions of curiosity given form. In the far side's unbroken stillness, our machines hum softly, keeping vigil for us all. They are bridges of light in a universe made of night. And from those bridges, new possibilities unfold, scientific, poetic, eternal. The far side of the moon has always been a paradox, a place both hidden and revealing, silent yet full of information. In the stillness beyond radio contact, in the gray terrain, unlit by Earthlight, lies a world uniquely suited for listening, observing, and remembering. Where the near side reflects the presence of Earth, the far side reflects the presence of everything else, the broader cosmos untouched by interference. After solving the challenges of distance and darkness, our gaze returns not just to what we can reach, but to what we can learn. The far side is not only a destination, it is a laboratory, ancient, quiet, and waiting. Silence is the far side's most valuable resource. Shielded by the moon's bulk, it is the only place in the inner solar system completely free from human-made radio noise. No signals from satellites, no transmissions from cities, no electromagnetic hum of technology. Only the natural frequencies of the universe itself, long, slow waves from cosmic dawn drifting through space for over 13 billion years. This silence is not emptiness, it is clarity, a medium through which the universe speaks in whispers. Astronomers dream of listening from there beyond the noise of Earth. The far side could host low-frequency radio observatories instruments that hear wavelengths too long to penetrate our ionosphere. These are the ancient echoes of the early universe vibrations from the time before stars were born, the so-called dark ages of cosmology. By listening to that faint background, scientists could trace how the first atoms formed, how gravity gathered them into galaxies, how light first awakened in the cosmic night. The far side of the moon may become one day humanity's ear pressed to the earliest heartbeat of the cosmos. Imagine a wide crater on the far side, its rim tall enough to block stray signals from above the horizon. Inside, engineers unfold delicate antennas made of thin wire, spreading them like vines across the regolith. They shimmer faintly under the distant sun. Each antenna catches radio waves between 1 and 30 megahertz frequencies long ignored by telescopes on Earth. Each pulse it receives is ancient light, slowed into sound arriving from the farthest reaches of time. Such an observatory could reveal what no optical telescope can see, not the shining galaxies, but the universe before light itself. The period when hydrogen atoms cooled, when the first stars had not yet formed, when the cosmos was filled with a diffuse fog of creation. The far side's radio silence is a cosmic treasure, and to use it requires only patience and respect to listen gently, not to disturb. Future concepts like NASA's Lunar Crater Radio Telescope, LCRT, imagine building an immense dish across a far-side crater suspended by lightweight cables. No walls, no domes, just wire dust and light. A listening instrument vast enough to hear the universe breathe. Beneath the listening silence lies another kind of record, a geological archive that has never been erased. The far side's crust, thicker and older than its twin hemisphere, preserves the early history of the moon and, by extension, of Earth. When asteroids struck during the late heavy bombardment, fragments of those impacts settled here and stayed undisturbed. The near side, softened by lava flows, lost many of its earliest scars. But the far side remained static, like a page never rewritten. Studying its rocks and craters gives scientists a timeline of the solar system's youth, when collisions shaped planets, when orbits stabilized, when life's conditions were forming on Earth. Each layer of dust, each melt deposit, each fracture in the crust tells of that formative chaos. If we could take samples from several depths from basin floors, crater rims, and shadowed regions, we could reconstruct a near-complete history of lunar evolution. This is why robotic drills, landers, and future human missions aim for the far side's oldest terrains. The Moon, in its quiet rotation, holds the record of our beginnings, and the far side, untouched for eons, is the most faithful librarian of that record. At the poles, where sunlight barely grazes the horizon, the cold is absolute. Temperatures drop below 230 degrees C, low enough to trap volatile compounds in the soil. Here in the far side's southern reaches inside the South Pole, Aitken Basin, sunlight never touches certain crater floors. These permanently shadowed regions act as freezers from the birth of the solar system. Inside them, orbiters have detected hydrogen signatures, suggesting deposits of water ice and perhaps other frozen molecules: carbon dioxide, ammonia, methane. Each frozen molecule is a messenger, a sample of what comets and asteroids delivered long ago. By studying them, we learn how water arrived not only on the Moon, but on Earth. Future missions may send small rovers equipped with heated drills and spectrometers. They will melt small samples, analyze vapor, and read the story written in frost. The far side's ice is not abundant yet. Even a thin layer holds immense meaning. It speaks of survival of molecules that endured 4 billion years of cold waiting to be found. Another mystery hidden in the far side's crust is its magnetism. Though the Moon lacks a global magnetic field today, patches of magnetized rock remain remnants of an earlier era when its core may have generated a dynamo like Earth's. Some of these patches are stronger on the far side, clustered around impact basins and ancient lava flows. They suggest that when massive objects struck the Moon, they altered its magnetic and thermal balance, creating local anomalies that still persist. Studying these regions can reveal how small planetary bodies cool and evolve. If the Moon once had a molten rotating core capable of generating a magnetic field, that field's extinction tells us how quickly heat escapes from such a world, and why some planets sustain life while others freeze into stillness. Magnetism is memory made visible, invisible lines that once danced through molten rock, now fossilized in stone. To measure them is to listen not with ears, but with instruments that sense the faintest magnetic pulse, like the last echo of a long, quiet song. One of the most delicate experiments yet to be expanded on the far side is lunar seismology. During Apollo, astronauts placed seismometers on the near side which recorded the Moon's subtle tremors from meteor impacts, from the tides raised by Earth's gravity, and even from thermal contraction during lunar night. The far side, however, remains largely silent to such listening. No instruments have yet stood there to measure its inner motion. If future missions place a network of seismometers across both hemispheres, scientists could map the Moon's internal layers with precision, its crust mantle and core, each vibrating with distinct frequencies. By listening to these faint quakes, we could understand the Moon as a whole organism, a sphere with its own rhythm and breath. We might even detect the lingering reverberations of the South Pole Aitken impact itself, still echoing deep within. Seismology in this sense is a kind of cosmic meditation, a listening to the heartbeat of stone. Though barren, the far side offers lessons for life. Its surface is unprotected from radiation, unshielded from micrometeorites, and exposed to extreme temperature swings. These conditions resemble those of early Mars or of exoplanets orbiting close to their stars. By studying how organic molecules or microbes survive or degrade when exposed to this harshness, we can prepare for interplanetary habitats and long-duration missions. Some future experiments plan to send sealed biological payloads to the far side small ecosystems in capsules to test how seeds, bacteria, or DNA endure lunar cycles. They will not contaminate the moon. They will simply observe how life behaves in silence. If we can preserve life there, even for short periods, it strengthens our understanding of resilience, how life persists, adapts, and transforms. In the stillness of the far side, life's fragility becomes its own strength, a reminder that existence endures even when nothing invites it. The far side also offers practical potential. In addition to ice, it contains minerals such as ilmenite olivine and plagioclase rich in titanium and oxygen. These materials could one day support in situ resource utilization ISRU, the art of using what is already there. Oxygen could be extracted from regolith to produce breathable air or oxidizers for fuel. Metals could build structures or shield habitats. Water ice split into hydrogen, and oxygen could become rocket fuel for journeys outward. The far side's location also offers a vantage point free from Earth's gravitational clutter. It could host telescopes and communication relays for missions deeper into space. In this way, the far side becomes not an endpoint, but a launch pad, a stepping stone toward the outer planets, a gateway from the inner solar system to the wide unknown. Each resource we uncover brings humanity one step closer to sustainability beyond Earth, a quiet evolution from visitor to participant in the cosmic landscape. The far side's airlessness makes it an ideal detector for cosmic radiation. With no atmosphere to block high-energy particles, instruments placed on the surface can directly measure cosmic rays, solar wind, and interplanetary plasma. By tracking their arrival, scientists can study how the sun's activity shapes space weather, vital knowledge for protecting future astronauts and satellites. The moon thus becomes a shield of understanding, teaching us how to endure radiation's invisible storm. Beyond practical protection, these measurements offer clues about the origins of cosmic rays themselves. Particles accelerated to near light speed by distant supernovae or black holes. In their arrival, we glimpse the energy of galaxies. Every cosmic ray that strikes the far side is a traveler from beyond imagination ending its journey on a silent plain of dust. By studying their paths, we trace the map of the universe's most energetic events. From geology to cosmology, from chemistry to radiation, the far side of the moon stands as a confluence of science and serenity. Each discovery deepens our understanding not only of the moon, but of ourselves, of how curiosity shapes endurance, and how patience reveals truth. Future generations may see the far side transformed by subtle human presence. Small habitats, observatories, arrays of antennas tracing the hum of the early universe. But it will remain quiet. No cities, no glare, no noise. Just the slow turning of a world in shadow, continuing its orbit as it always has. In that environment, science and peace become the same act, the pursuit of knowledge without disturbance. The far side does not need to be conquered. It needs to be understood. When we look at the far side, we are looking at stillness incarnate. Every crater is an experiment already performed. Every rock is a record already written. Every silence is a signal waiting to be heard. The scientific potential of the far side is vast, not because of what we can add to it, but because of what we can receive from it. It asks nothing of us but attention to listen carefully, to move gently, to see what has always been there. In the grand rhythm of the solar system, the moon turns steadily, one face toward Earth, one away. And as we continue to explore that hidden hemisphere, we discover something familiar, that knowledge and stillness are not opposites. They are companions, like the near side and the far side, always bound, always in balance. The far side holds the silence of beginnings. It carries the memory of the first impacts, the chemistry of the first water, the whispers of the first light. In its quiet orbit, it invites us to listen not only to the universe beyond, but to the patience within. And so, as we look outward from our world toward that invisible half, we understand a little more of both. The universe continues vast and calm, and through the moon's quiet face turned away, we learn to hear it. The far side of the moon turns still unseen beneath the gaze of Earth. It has always turned slowly, silently, obedient to gravity's rhythm. For billions of years it faced the stars, while the near side faced us, two halves of one body bound by the same motion. And now, after centuries of myth, decades of exploration, and generations of dreaming, we understand what once hid behind the dark. The far side is not mystery defeated, it is mystery revealed. And in its revelation we find both knowledge and calm. When we first looked up at the night sky, the moon was a symbol, a pale disk hung above the horizon, serene and changeable. It guided calendars and tides, inspired poems and prayers. Its hidden face was the realm of imagination, home to gods, spirits, and impossible light. But science did not destroy that magic. It transformed it. Now we know that the moon's two sides are not equal. One is thin, smooth, volcanic. The other, thick, rugged, ancient. Their difference is written into the moon's birth, preserved in rock and silence. The near side, forever gazing toward Earth, carries the marks of volcanic fire and flowing basalt. The far side, turned outward, bears the scars of bombardment and time. Together, they form a single record, one side shaped by motion, the other by memory. In learning their nature, we see the same duality reflected in ourselves. We too have our illuminated faces, the visible, the known, and our far sides, quiet and unseen, holding the weight of history. Every step of our journey to the far side began with wonder. Luna 3's first faint photographs, the ghostly shapes of mountains and craters. Apollo 8's human eyes watching the Earth rise over a barren horizon, surveyors' delicate landing on dust that had never been touched, and the patient orbiters mapping every contour of light and shadow. Each mission added a single layer of clarity, as if focus itself were slowly sharpening. The moon became not merely an object in the sky, but a world alive with geology, silence, and meaning. And yet, even as knowledge deepened, wonder remained. Science, after all, does not erase mystery. It refines it. Each discovery only shifts the boundary of the unknown a little farther outward. Now the mysteries of the moon are no longer hidden behind distance, but beneath depth, beneath rock, beneath time, beneath the surface of our own questions. To reach the far side required invention, precision, and patience. Communication relays orbit above it, now small satellites, poised like lanterns in permanent twilight. Rovers crawl across its soil measuring spectra of light, counting grains of dust. Orbiters map gravity fields, revealing the hidden scars beneath. Each signal that crosses that distance is a quiet act of connection, a line of light threading through emptiness. When Queqiao relays a photograph from the Chang'e 4 rover, or when Lunar Reconnaissance Orbiter transmits data from its instruments, it is not just information traveling, it is curiosity given form. These bridges of radio and light carry more than data. They carry meaning. They remind us that knowledge is not born in isolation. It must travel, it must connect. The far side cannot speak to Earth without help, and neither can we know without reaching outward. Science in that way is its own kind of bridge building between worlds, between centuries, between the seen and the unseen. Before telescopes, the unseen half of the moon belonged to legend. Ancient civilizations filled it with stories, lands of light hidden gods, spirits of the dead. In China, it was the palace of Chang'e, the moon goddess. In Greece, the chariot of Selene. In the Islamic world, a mirror of divine beauty. Each story was a way of giving voice to the unknowable. And though we now speak in the language of physics and orbit, the poetry remains beneath the equations. When modern China named its lunar program Chang'e, it was not nostalgia, it was continuity. Science and myth, hand in hand, turning the same orbit. The far side still holds its mythic quality even under the scrutiny of instruments. The silence is real. The solitude is profound, and those who see it even through screens and sensors still feel the hum of something beyond measurement. It reminds us that the universe does not lose its mystery when we understand it. It gains dimension. In every era, the moon has mirrored the state of our imagination. Once it was the unreachable. Then it became the goal. Now it is the beginning, the first step toward other worlds. The far side reflects not just light from the sun, but our evolving understanding of ourselves. To explore it is to see what humanity can become when it listens patiently, when it learns without haste. Each crater and plain, each scar and basin shows how endurance shapes beauty. Even destruction becomes pattern. Even silence becomes story. If the moon is our mirror, then the far side is the part of us that dreams quietly, the part that learns by waiting, that grows by observing. The exploration of the far side is far from over. Every generation adds another orbit, another experiment, another image. Soon, humans may return to the moon with Artemis perhaps to build habitats on the rim of the South Pole Aitken Basin, where sunlight and shadow meet in perfect balance. From those bases, astronauts might conduct radio astronomy in the dark plains below, collect frozen water from eternal shadows, and study the moon's deep structure with instruments far more sensitive than Apollo's. Their work will continue what began in the 20th century, but with a different purpose. Not a race, not a conquest, but a collaboration with silence. The far side is not a frontier to be claimed. It is a teacher to be heard. As technology becomes quieter, more autonomous, more sustainable, Our exploration begins to resemble the moon itself, measured rhythmic calm. The relationship between Earth and Moon is not static, it is a dialogue. Each influences the other's tide spins and stability. Earth's gravity locks the Moon's face. The Moon's gravity tugs at Earth's oceans, shaping life's rhythms. Through that gentle exchange, both bodies have evolved together a duet written across billions of years. The far side, though unseen, is part of that duet. Its silence balances our sound. Its distance balances our closeness. Without it, the Moon's orbit and perhaps Earth's own stability would be different. Even now, as we explore it, we are participating in that ancient conversation. Every signal that crosses the void is an echo of that gravitational whisper between planet and satellite, between home and horizon. It reminds us that we too are part of the same rhythm, turning and being turned, seeing and being seen. Science often speaks in the language of matter, mass, heat, energy, motion. But beneath those measurements lies narrative, the transformation of chaos into order of question, into understanding. The far side of the Moon tells such a story. A story of impact and endurance, of frozen time and patient observation. A story of light taking billions of years to arrive and finding at last a listening ear. It is a story without conflict, yet full of motion. A story in which destruction and beauty share the same source. The South Pole. Aitken Basin tells of a collision so vast it nearly split the Moon apart. Yet, from that event came knowledge of the Moon's interior, a glimpse into the mantle itself. Every crater, every shadow, every trace of ice is a chapter written in the same steady tone: change, endure, reveal. If the near side is the face of the Moon, the far side is its memory. And memory, like orbit, never truly ends. It only circles, returning again and again to the same points of reflection. Our exploration of the far side is not just a scientific chronicle, it is a human one. It carries the voices of countless people: mathematicians, engineers, pilots, poets, technicians, dreamers. Some looked through telescopes, others through computer screens, others from within spacecraft windows. Each contributed a line to the same quiet poem: to see what lies beyond the visible. When Frank Borman, orbiting Apollo 8, described the far side as a vast, lonely expanse, he was not describing despair, but reverence. When Michael Collins drifted behind the Moon, cut off from Earth, he found peace in solitude. When the Chang'e engineers received their first signal from the von Karman crater, they heard the voice of patience returning from silence. The far side connects them all, past and future, east and west, human and machine. It is a shared field of curiosity, bound by gravity, illuminated by thought. From myth to mathematics, from the first stone calendars to laser altimeters, our understanding of the Moon has come full circle. We began with wonder, and returned to it now refined by clarity. The circle of knowledge, like the Moon's orbit, is continuous. There is no end, only phases, transitions of light and shadow. We look up at the Moon tonight, knowing what lies beyond its face, yet it still feels mysterious. The far side's craters are mapped, its minerals catalogued, its silence measured, and still it remains unreachable by sight. It continues to turn away, as it always has, reminding us that the universe will always have another side. Knowledge, too, has a far side, a region forever just beyond our knowing. It is that distance which keeps us searching. The moon's hidden hemisphere teaches many things: that silence is not emptiness but preservation, that endurance is a form of beauty, that curiosity, when patient, becomes wisdom. It shows that even in isolation, connection can exist. Even in darkness, reflection continues. Perhaps that is the far side's truest message. That knowledge and stillness are not opposites. They coexist as Earth and Moon do, turning in harmony, bound by unseen force, each defining the other. The far side's craters hold the memory of impacts. Our hearts hold the memory of discovery. Both are shaped by collision. Both endure by motion. Now, as we drift back from this long journey from myth to exploration, from machinery to meaning, let the mind settle again. The moon continues its orbit serene and unhurried. The earth turns beneath it, drawing tides, shaping light. Between them, space hums with quiet energy, invisible yet constant. You have traveled across that space tonight, through history and time, through silence and illumination. You have stood on the edge of the South Pole. Aitken Basin, listened to the hum of radio silence, watched the first light fall over craters no eye once saw. And now the orbit closes. The far side fades again behind the horizon of imagination, where it belongs, not lost, but resting. The far side of the moon will keep turning. The relay satellites will keep circling. The dust will keep shining softly in sunlight that has crossed 150 million kilometers to arrive. Even as we sleep, that motion continues. The universe moves with quiet precision, indifferent yet harmonious. In that motion lies comfort that everything endures. Everything belongs. Everything is connected by gravity and light. So rest now beneath the same sky that holds the moon. Its hidden face faces away, but its rhythm touches you still. The same force that keeps it bound to Earth holds you softly within the same unfolding of space and time. The far side is unseen, but not unknown. Its silence continues. Its beauty remains, and the night carries on calm, endless, eternal. You have traveled far tonight, across light and shadow, across time and silence, through the slow breath of the moon and the long patience of its turning. Now let everything grow still again. Let the images of craters and silver plains fade gently, like tides receding into dark water. There is no need to hold them. They will remain orbiting softly within the mind. Above you, the same moon continues to move slow, steady, unhurried. Its far side drifts unseen, yet the rhythm of its turning touches the earth, pulling at the seas, drawing at your breath. Somewhere beyond sunlight glances across the rim of the South Pole Aitken Basin, and dust rises in a silence so complete it has never known a sound. The relay satellites trace their paths like fireflies of metal and memory. The universe turns endless and calm. You are part of that motion, bound by the same gravity, stilled by the same dark. There is no distance between you and the moon, only space filled with quiet. Let that quiet deepen now. Let the mind drift where it will, through shadow, through light, through the soft hum of everything continuing. No need to think of discovery or time or names. only the slow rhythm of the orbit, the gentle pull that keeps one world near another. The stars move, the moon turns, the night breathes. And you are still floating within it all. Rest now. The universe will keep turning.